In this video, we're going to talk about bond energy. So bond energy is the amount of energy required to break a chemical bond. That's the simple definition. So let's take this for example. So I have a molecule A, and then I have a molecule B, and then there's like a bond here. And its bond energy is, let's say, 400 kilojoule, okay? 400 kilojoule per mole. What this means is that to break 1 mole of this bond right there, it will cost 400 kilojoule. That's all it means. So kilojoule, remember, it's a unit of energy, and mole, it's a quantity. 6.23 times 10 to the power of 23. That's 1 mole. So in a chemical reaction, we don't just like break bonds, we also form new bonds. So like consider this reaction here. It takes energy to break these bonds, but when we like add energy to break the bond, there's a product forming, which is over here. So there's like a net happening here. We lose and gain energy. And there's a formula where we can calculate the energy change in a chemical reaction. Delta H is equal to the sum of all the energy required to break the bond, which is the reactant side, plus the sum of all the energy released in the formation of new bonds, so which is the product side. And because this one is released, we can consider them negative because we lose energy. So we can just put a minus as well because we lose energy anyways. And you also need to know the difference between endothermic and exothermic reaction. So an endothermic reaction is if the amount of energy required to break the bond is greater than the amount of energy released, then it's an endothermic reaction. So like the system gains energy. So like it's absorbing heat. And an exothermic reaction is if the amount of energy released is greater than the amount of energy required to break the bond, then it's an exothermic reaction. So the system, there's a net loss of energy. So it's like giving away that energy. It's like it's giving away heat. Let's calculate the energy change using bond energy. So consider this reaction here. And the bond energy for H bond is 432 kilojoule per mole, and the bond energy for OH bond is 467 kilojoule per mole. So when calculating the bond energy, I recommend you to like first draw its structure. So water would be like this, and we don't need to like care about the lone pair because that's not the deal right now. We care about the bond, and we know we have 2 of these. So if it takes 467 kilojoule to break one of this, then how much will it take to break all of this? So we know there's 1, 2. So per 1 mole of water, there's like 2 OH bond here. So, and then we multiply by 2. So we have 4 mole in total. So we have 4 mole in total. And then we multiply by this number here, the bond energy. So it's going to be 467 kilojoule per mole. And notice that the unit moles cancels out. This is what we exactly want because it's a bond energy. So 4 times 467 is 1868 kilojoule. That's the amount of energy it takes to break the bond. And now for hydrogen, the bond energy is 432 as shown here. So hydrogen would look like this. And then there's like two of them. So we know that it takes 432 kilojoule per mole. So like 432 kilojoule to break one of this. And there's two of that. So times 2 mole. The units cancels out. The mole cancels out. That's good. And now 432 times 2 is going to be 864 kilojoule. And we're not done yet because we need to find the bond energy for this, which I forgot to show you, but for O2, the bond energy is 498 kilojoule per mole. So we only have 1 mole of oxygen, and this is the bond energy. So to calculate 498 kilojoule per mole times 1 mole, the mole cancels, which is just 498 kilojoule. And we have to add these two here. So the total energy release is 864 plus 498, which is 1362 kilojoule. Now the net energy change will be, so delta H is equal to reactants, the total energy of reactants minus the product, which is 1868 kilojoule minus 1362 kilojoule. And this gives us, which is 506 kilojoule. So this is the final answer. That's the enthalpy change of the reaction, the decomposition of water. This is an endothermic reaction since the reactant was greater than the product, the energy. On an energy diagram, a endothermic reaction will look something like this. And this is the energy change, which was 506. So on a water, it will look like this. And this is time. This is energy. And this is going to be the reactant. And this is the product. By the way, the reason why the reactant was at the start is because in the start of the chemical reaction, you only have the reactants. That's why. And then in the end, you only have the product there. Consider this reaction. Use the bond energies to calculate the enthalpy of this reaction. So let's start with methane. So let's draw what it looks like. So a methane looks like this. So carbon, hydrogen, and hydrogen. And we are given the bond energy for carbon hydrogen, which is 413 kilojoule per mole. So 413 kilojoule per mole. And then we have to multiply by 4 mole because there's 4 of these carbon hydrogen bond. So 413 times 4, the mole cancels out. And then on your calculator, you should get, which is 1652 kilojoule. And now with oxygen, so oxygen looks like this, diatomic. And we have 2 mole of that, so we have to keep in mind there's 2 mole of that. And we are given the bond energy for oxygen, which is 498 kilojoule per mole. So it's going to be 498 kilojoule per mole times, and there's 2 moles, so 2 mole. The unit mole cancels. So 498 times 2, this gives 996 kilojoule. And we can add these up now. So 996 plus 1652 is, so 2648 kilojoules. So this is the total energy required to break these bonds. And now let's calculate how much energy is formed. Carbon dioxide looks like this. So CO double bond. And we are given the bond energy for carbon dioxide. So this is 799 kilojoule per mole. And there's 2 of these bond here. So 799 kilojoule per mole times 2 moles, because there's 2 bond of them, which is 1598 kilojoule. So this is how much energy you're formed by just carbon dioxide. Let's focus on the water now. So water looks like this. I'm just ignoring the electrons because it's not that important here. And remember, we have 2 mole of this. And the bond energies for OH bond is 467 kilojoule per mole. So 467 kilojoule per mole multiplied by, so in each mole of water, there's 2 of OH bond and there's 2 of them. So 2 times 2 is 4. So we have 4 mole. And now these cancels. So 467 times 4, which is 1868 kilojoule. So this is how much energy is from the water. And now we can add these 2 up. 1868 plus 1598 should give 3466 kilojoule. This is how much energy is formed from this. Now we need to find the delta H, the enthalpy. So delta H is equal to the energy of reactant, which is 2648 kilojoule, minus this thing here, so 3466 kilojoule, and then we should get negative 818 kilojoule. So we lost energy this time. So that means this is an exothermic reaction. We're losing heat. And this makes sense because this reaction that you see here is a combustion reaction. And a combustion reaction is always exothermic because that's what we need them for, because they give away heat. Now, so the exothermic reaction on an energy diagram will look something like this. So you'll start from like here, and then it goes down all the way like that. The enthalpy change, delta H, is negative here. So last time, we had negative 818 kilojoule for our reaction. So it's here. So we have a net loss of that energy. And you have a product here and then a reactant. This is always energy, and then this is time. This is what it looks like. And you should also know how to write the thermochemical equation. So for exothermic reaction, the thermochemical equation, the delta H is always on the product side. So let's do one for our previous reaction that we just did. So carbon plus oxygen, which forms water and carbon dioxide. Since this is an exothermic reaction, on thermochemical reaction, the enthalpy change is always going to be on the product side. So plus 818 kilojoule. This shows that the energy is being released. So an exothermic reaction also, you have something in here. During exothermic reaction, the system loses heat, so it just gives off heat to its surrounding. This means that the surrounding is becoming hotter while this thing right here is losing heat. Everything else is getting hotter though. Now try this problem for yourself. So feel free to pause the video and give it a go. And let me give you a hint. So this is a combustion reaction. So the enthalpy change must be negative. So meaning your answer has to be like a negative kilojoules. So let's start with propane over here. So we have carbon bond here and then another carbon bond here. And we're given the bond energy for carbon, which is 347 kilojoule per mole. And we have just 1 mole of propane here. So we have 347 kilojoule per mole times 2 mole, because we have this bond here and this bond, so this 2 bond. And for the carbon-hydrogen bond, the bond energy is 413 kilojoule per mole. So there's 1, 2, 3, 4, 5, 6, 7, and 8. So there's 8 of these bond. So 413 kilojoule per mole times 8 mole. Yes, this is what we exactly want, because so these unit moles could cancel out like that. And then this should give 694 kilojoule. Now 413 times 8 is 3,304, and kilojoule, of course. So this number here is the bond energy to break propane. That's the energy we need to break a mole of propane. And now for oxygen, so we have 5 mole of oxygen gas, of course, and then this is the bond energy, so 498. So 498 kilojoule per mole times 5 mole, because there's 5 mole of oxygen and there's only 1 bond in each mole. So this should give, mole cancels again, 498 times 5 is 2,490 kilojoule. So this is the total energy required to break 5 mole of oxygen. And this whole thing is the total energy needed to break the reactants bond. And the whole thing adds up to 2490 plus 3304 plus 694, which gives 6,488 kilojoule. Now let's focus on the product side. So this thing. So we have 3 mole of our carbon dioxide, and a carbon dioxide bond energy is 799. So we have 799 kilojoule per mole times. So we have 3 mole of carbon dioxide, but each mole, so we have 2 of these carbon oxygen bond. So we have 2 mole times 3, so which gives 6 mole. I don't know why the color is in red, but yeah. So these cancels. So 799 times 6 is equal to 4,794 kilojoule. And now for water. So we have OH bond and OH bond. So we have 2 OH bond per mole of water. And there's 4 moles, so 2 times 4 is 8. So, and the bond energy for OH is 467 kilojoule per mole. 467 kilojoule per mole times 8 mole. We have 8 mole of that OH bond. So the unit mole cancels again. 467 times 8. This gives 3,736 kilojoule. So if I add these two up, so 3736 plus 4794, this gives 8,530 kilojoule. So this is the total energy formed by the product. Now the enthalpy change is the reactants minus the product. So delta H is equal to 6,488 kilojoule minus, that was a horrible looking minus, yeah, like minus 8,530 kilojoule. And delta H, the enthalpy change, is so 6,488 minus 8,530 kilojoule, of course, and then this gives negative 2,042 kilojoule. So this is the enthalpy change of this reaction. Determine the enthalpy change and write the thermochemical equation for the formation of ammonia from its element. So to begin, we must always start with the chemical equation, like a balance equation. So we have N2 plus H2, because these are elements, diatomic elements, and then this forms NH3. Now we balance it. So we have 2 nitrogen on one side and then just 1 nitrogen on the other side. So we'll add a 2 here. So because we added 2 here, now we have 6 hydrogen here because 3 times 2 is 6. So that means we must have 6 on the other side. So we'll simply add a 3 as the coefficient. So now we have a balanced reaction. Now we can use the bond energy to find the enthalpy change. So N2, it looks like this. And we'll just ignore the electron because it's not that important here. We just care about the bond. So we have 1 mole of this. And then we have 3 mole of just diatomic hydrogen. And now we have 2 mole of ammonia. So H and H, and we don't need electron, but if you want, I guess. since we only have 1 mole for this, we can simply just do 945 kilojoule per mole, because that's the bond energy that we're given here, times 1 mole, because there's only 1 mole. The unit mole cancels, and we're just left with 945 kilojoule. That's the amount of energy required to break 1 mole of nitrogen gas. And now for hydrogen gas, so we have 3 mole, and a hydrogen, the bond energy is 432 kilojoule per mole. So 432 kilojoule per mole times, and there's 3 mole of hydrogens. 3 mole, the unit mole cancels. So 432 times 3, this gives 1,296 kilojoule. Now for ammonium, we have NH bond here, and then NH bond here, and NH bond here. And we also have 2 mole of ammonia. So it's basically just 3 times 2. So 3 times 2 is just 6. And the bond energy for NH is just 391 kilojoule per mole. So 391 kilojoule per mole times 6 mole. So mole cancels, and then 391 times 6 is 2,346 kilojoule. Now we need to find the enthalpy change. So I'm gonna add these two up, because that's the total energy from the reactant side. So 945 plus 1,296. So we get 2,241 kilojoule. And then the enthalpy change is going to be this minus this. We get negative 105 kilojoule. So since we have a enthalpy change as a negative, that means this reaction is a exothermic reaction. So it loses heat, that gives its heat around its surrounding. And now, since it's an exothermic reaction, the enthalpy change is on the product side of the equation. So it'll be plus 105 kilojoule. And this is the thermochemical equation of ammonia, the formation of ammonia. And that's it for this video. Thanks for watching, and I'll see ya. Bye.